A few of the Unit 3.8 practice problems, not many, and this is how they represent what's happening in a solution. So you can see here, you've got ion dipole attractions between whatever these X and Y things are and the water molecules. You need to know that the face part of Mickey Mouse here is the oxygen and the little ears are hydrogens. So the fact that with X, I've got the partially positively charged hydrogens pointing towards X, that tells me X must have a negative charge. Over here with Y, I've got the partially negatively charged oxygens of the water molecules pointing at Y. Y must have a positive charge. So I expect X to be an anion, which has a negative charge, and Y to be a cation, which has a positive charge. Also notice they have made Y smaller than X. If you have to draw something and you have to break it into cations and anions, almost always your cation is going to be smaller than the anion. Because if you think about it, the cation has lost an entire outer energy level, and that makes them really small and tight. The anion has gained more electrons, and it makes it bigger and looser than the atom itself would be. So usually larger than the cation. So I am thinking, let's look at A. Ion X is sodium plus 1. Well, no, I expect X to be an anion. A's out. Same thing, ion X is sodium plus 1, B's out. Okay, I'm between C and D. They both say that X is chloride. And so what do I expect Y to be? I expect Y to be a cation. I would not expect to have two anions. So D's out. The answer here is C. Okay. The diagrams above for number 2 represent aqueous solutions of compound X at various molarities. Each dot represents 1 mole, and the volume of the solution in the large boxes is twice the volume in the small boxes. Which solution has the highest molarity? So I'm going to say the volume for the small boxes is 1 liter, and the volume for the large boxes is 2 liters. So for A, I've got 3 moles per 1 liter, so that's 3 molarity. For B, I've got 4 moles per 1 liter, so that's 4 molar. For C, I've got 6 moles for 2 liters, that is 3 molar. And for D, I've got 5 moles for 2 liters, that's 2.5. So the highest molarity is going to be, B. Okay, coming over here. Now, this is a pretty good representation, I think, of an ionic compound in the process of dissolving and dissociating. When you have a soluble ionic compound, the thing that breaks it apart really are the polar water molecules pulling it apart. And so with this image, you can see all of the hydrogens in these water molecules are kind of almost stuck on this larger thing. This will be an anion because it will have a negative charge, and that's what's attracting those partially positive charged hydrogens. Over here, this guy's smaller, and he's got the oxygen side of the water molecules pointing towards him. The oxygen side is partially negative. He must have a positive charge. He's going to be a cation. Again, notice they made the cation smaller than the anion. That's pretty common. Okay, so based on the orientation of water molecules, what can be assumed about the charge of the hydrated particle indicated by the arrow? So we're looking down here at this cation. Okay, right off the bat, I don't have to read a whole lot. I know it's positively charged, but that's why the oxygen atoms in the water are attracted to it. Also, so that is the answer. One other thing to, kind of mention here is that what is being represented by these images, and I think also these images over here, are called ion dipole attractions. It is a type of intermolecular force that is very specific to cations or anions, usually in solution, usually in water, and the water here is the dipole. Okay, thanks, guys.